Okay, starting at the top. When hydrogen and oxygen are mixed under certain conditions, H2O, water, will form. Students did the following experiments to study how H2O forms. All right, so if you haven't figured out what the reason for them doing this study is, it's to study how H2O forms. So I would go ahead and underline how H2O forms. Cool. So I've underlined that. And so we've successfully found the reason that they're going to perform this series of experiments. We get to go ahead and move on, and we're going to circle our method. So, Experiment 1. A thick-walled glass syringe fitted with a sparking device was filled with 20 milliliters of hydrogen gas, H2, and 10 milliliters of oxygen gas, O2, as shown in Figure 1. Okay, so that seems like its method, but we might have some more methods, so let's hold off for a second. And then we have Figure 1, and then it continues. The syringe plunger was then locked in place, and the gases were sparked. A reaction took place, forming droplets of water. The plunger was then released. The gas in the syringe was allowed to adjust to room temperature and pressure, and the final volume of gas was recorded. The remaining gas, if any, was then analyzed to determine its composition. The procedure was repeated with different volumes of gases, and the results were recorded in Table 1. Okay, so a lot of that is actually method. So what you'd want to do in this instance, where pretty much the whole paragraph is method, is kind of circle key pieces of information. So the explanation of, it's a thick-walled glass syringe fitted with a sparking device, etc., is also kind of in Figure 1. So I would circle things like 20 milliliters of hydrogen gas, 10 milliliters of oxygen gas. So we've got 20 ml H2 plus 10 ml O2. So I would be, circling these things. And then we also know, okay, we have a reaction, plunger was released, the gas in the syringe allowed to adjust to room temperature and pressure, and the volume of gas was recorded. So I would go ahead and circle that as well. So we have gas in syringe to recorded. Okay, and then it doesn't tell us how it was analyzed to determine composition, so pretty much these are our two really important key details in our method. So go ahead and circle those. Okay, and then we have Table 1. So obviously we can find Table 1 easily. That's not the point of making the asterisk, but it is important. So we make an asterisk and we look at Table 1. So we have 6 trials. We have a couple different initial amounts of hydrogen gas, a couple different initial amounts of oxygen gas, and then it gives us final hydrogen, final oxygen. Okay, so if we're looking at this, I would go ahead and look at, when we have final hydrogen, we only get excess hydrogen in the last trial, trial 6. So that draws my eye immediately, and that's a good idea to, look for little differences like that. So we have 50 of H2 and 20 of O2, and we have 10 left over. Okay, versus if we have 40 and 20, we have none left over. Okay, so 40 versus 20, it seems like we need twice as much H2 as O2, and that gives us what we want, nothing left over at all. Versus like if you look at trial 2, you have 20 H2 and 20 O2. If we're right that you need twice as much H2 as O2, there should be 10 O2 left over, which, yep, is confirmed by the table. So the relationship that you'd want to, notate somehow would be that you need 2 times as much O2, or sorry, H2 as O2. Okay, and then let's keep on reading. Since it is known that equal numbers of molecules of different gases occupy equal volumes at the same pressure and temperature, the following equation was suggested. 2H2 plus O2 equals, or translates into, 2H2O. Great! That's actually exactly the same relationship that we used in our table. So, yay, go team. All right, so we've got they proposed a equation, and we confirmed it with their table, the evidence that they have. So then we would go ahead and go through and say, okay, now we're at method 2. I'll go ahead and put 1 up by the first method. Okay, so method 2 is experiment 2. In the apparatus shown in figure 2, a stream of H2 is passed over hot copper oxide, CO, producing H2O vapor. The vapor was then absorbed by calcium chloride. Okay. The changes in the masses of the tube sections containing, sorry, I lost my place. Oh, here we go. Containing the copper oxide and calcium chloride were used to calculate the mass of copper oxide reacted and the mass of H2O formed. It was determined that 1 molecule of H2O was produced for every copper oxide reacted. Okay, so again, in the method, we're going to look at, how they did it. So if we're looking for how they did it, that would be in the first part, because the next part just explains how, basically the methods. We don't have a nice table for this one, unfortunately. So we would want to circle basically the first part. First part of this is our method. And then our results, this time, we don't have a table, but we do have the equation. So the equation is, similar to when we had table 1, we figured out the equation. They figured out the equation, so we actually could make a table if we wanted to. So everything is even, which is nice and easy. Okay, cool. So let's go ahead and look at the questions next. So hopefully everybody has, taken notes, marked up their passage, etc. in a similar way, because I'm going to have to erase the screen so that we have space to actually, look at the questions. So I'll give everybody a couple more seconds to go ahead and, make sure they've written down notes. You also could pause the video and, do it that way. Okay, so we have 6 questions, and that's actually pretty much the average number of questions that you're going to see, because it's 5 through 7. So let's go ahead and start at the beginning and work through them. So first question, which I know it seems a little bit weird, but it's from a real test, and that's why it's question 30 instead of question 1. So question 30. When an electric current is passed through H2O, the H2O decomposes to form H2 and O2. Okay, makes sense. It's exactly the opposite reaction of what we already looked at. Which of the following correctly represents this reaction? Okay, so it should be just the opposite of the equation that we already have. So we had 2H2 plus O2 is 2H2O. So we should just start with 2H2O, and, so you'd have 2H2O arrow, 2H2 plus 2O2. So you should have something like this, 2H2O, should give you 2H2 plus 1O2. So let's go ahead and look at the answers. So F and G don't start with water, and we have to start with the thing that, it tells us to start with. And so we are left with H and J. So both of them start with 2H2O, that's good. But J mixes up the relationship and says you need 2 oxygen for every hydrogen, which isn't how it works out. So H is our correct answer. So see, if we've already marked everything up and we understand what's going on, it's really fast and easy to do that. Okay, 31. In trial 1 of experiment 1, after the reaction had taken place, but before the syringe plunger was unlocked, one would predict that, compared to the pressure in the syringe before the spark, the pressure in the syringe after the spark was... Okay, so we're trying to figure out, was it higher, was it lower? So, after the reaction had taken place, when the reaction takes place, we now have water, right? Depending on how much H2 and O2 we started with, we might have some excess gas as well. But as long as we started with at least some of both of them, we should have some water. So there's more water, less gas. And only gas is in our plunger, right? So if we have more water, less gas, we should have less pressure as well because there's less material, let's say, in the plunger. So less gas equals less pressure. So let's go ahead and look at the answers. So A and B are both lower, so we can keep those, and we'd immediately know that C and D are wrong. So we have lower because the overall amount of gas decreased. Ding, ding, ding. Lower because the overall amount of gas increased. No. So A is our answer. Now, that does require some small amount of scientific knowledge to know that, the more of something you have, the more pressure you have. But even if science isn't really your forte, it logically makes sense. So the more of any material you pack into a small amount of space, the more pressure is on it. It's why, let's say you're trying to pack a Tupperware overly full, it's not going to close at some point because there's just not enough physical volume to accommodate whatever you're trying to put in it. Too much pressure. Okay, next one is 32. If 50 milliliters of H2 and 50 milliliters of O2 were reacted using the procedure from experiment 1, the final volume of O2 would most likely be... Okay, so we said we need twice as much H2 as O2. So if we have 50 H2, then we would want to add 25 because that's half as much O2. So since we're not adding 25, we're adding 50, our answer should be 50 minus 25, which is 25. So if we look at our answer choices, J is the only one that gives us 25 milliliters. So that's our right answer. All right, moving on to 33. Which of the following assumptions about the chemical reactions in experiment 1 were made before the final measurements were taken? Okay, so far we've been, kind of reading our table, understanding, using little patterns. This is scientific reasoning, pure and simple. So we're trying to figure out what assumption the researchers made while they were doing their experiment. So, the final measurements are taken after, let's see, the gas in the syringe was allowed to adjust to room temperature and pressure, and the final volume of gas was recorded. Okay, so that's the part we actually circled that because we knew it was going to be important. So, they thought there was a reaction and then they recorded it. So the assumption is that, the reaction took place. So let's see. Excess O2 must be present for water to form. Okay, that is random. And also not true because, even when you have, for example, like trial 1, trial 5, and trial 6, there's not excess oxygen, but water still forms. Okay, our next one is related to experiment 2. We don't talk about copper oxide in experiment 1, so as soon as you see that, it should get crossed out. H2 is not absorbed. Oh, okay, again, calcium chloride shows up, and we did not talk about that in experiment 1, so B and C are out for being totally out of scope. And then D, each reaction had run to completion. Now that makes sense, matches our prediction. They wouldn't have taken measurements if they thought that the reactions were not finished. So they took them when they thought that everything was done. All right, 34. When nitrogen gas N2 is reacted with H2 under certain conditions, the following reaction occurs. So you have one nitrogen molecule, milliliter, etc., 3 of hydrogen, and you get 2 NH3. Awesome. Based on the result of experiment 1, if 10 milliliters of N2 were completely reacted with 40 milliliters of H2 at the same pressure and temperature, what volume of H2 would remain unreacted? So we're going to use we're going to use the information that they just gave us to figure this out. So we have 10 N2, and then if we have 1 N2 and 3 H2, we should have 30 H2 to give us our reaction. But instead of 30, they told us we had 40. So our leftover is going to be 40 minus 30, which is 10. So our answer should be 10. And that would match with G. So I purposely actually picked this passage because this is the most science knowledge-based passage that pretty much I've seen. Most of them you literally don't have to have any science knowledge at all, but this one, if you had a teeny tiny background in chem, stoichiometry, you would probably understand this faster than if you've never taken chem, you've never seen chemical reactions, you hate chem and it really confuses you. But the idea is they give you the equation and you're just plugging in. So if I have 1 N2 for every 3 H2, if I now have 10, I should have 30, and they gave me 40, so 10 is left. Okay, and the last one. Which of the following, if it had occurred, would probably not have caused an error in interpreting the results of experiment 2? Okay, so this is hard because we have to actually look at all of the answers before we can come up with our final answer. And also it's difficult because it's a not question. So immediately whenever you see it not, you want to underline it, circle it, star it, do something so that you make sure you don't accidentally answer the opposite of that. So we want something to not cause an error. So we want no error. So 3 of them will be things that would cause errors. 1 will be something where it really wouldn't affect anything. So the first one, using H2 contaminated with non-reactive impurities. Okay, well, if there's non-reactive impurities, then those wouldn't react with the O2, which means it wouldn't cause a difference in the resulting amount of water or H2 that was left in the syringe at the very end. Or actually, sorry, look at me. I did not see experiment 2. Same exact theory, but we're looking at different chemicals, so we're not dealing with O2. But again, same thing. If you use H2 that has non-reactive impurities, it's not going to react with copper oxide, which means it's not going to affect how much calcium chloride we're going to see in the final reading. Okay, so A is looking pretty darn good, but let's look at the other ones. So next one is using copper oxide contaminated with reactive impurities. Okay, that means that we have copper oxide and we have something else that reacts with H2, which means that that's going to totally throw off our equation. So B is a big issue, but since this is a weird not question, B can be crossed out. Okay, C, H2O escaping without being absorbed by your calcium chloride. Okay, if water is escaping, that is changing our reaction, because again, if you just look at the very last line in your experiment 2, we have a chemical reaction, and part of it is water. So if water is escaping, that's changing our reaction. And then D, other reactions occurring between copper oxide and hydrogen that produced different products. Okay, so if they're producing different products, that's going to change our equation up. That's going to be a big problem. So the only one that is not a problem is answer choice A. Okay, so there you have it. That is how you would go ahead and work through a research summary passage. Remember, there's 3 out of every 7 of them are going to be research summary, so they're very important. And basically, you want to follow that same exact idea every time that you're working through them. So watch out for the difficult patterns questions with how new variables would react. Watch out, which by the way was like 34 was just totally new variables, but using the same idea that you learned in the passage. And watch out for the scientific reasoning ones, because those can be pretty difficult, especially the new experiment. Okay, so you guys did a really, really good job. And if you're at all unsure of any of the question types or how to deal with them, some of these same question types are going to show up on the next video. So go ahead and also watch the data representation video. Just in general, if you're prepping for this test, you should watch all the videos, but especially if you're confused about anything in this video, because the next one is going to also cover some of the same stuff and also a lot of new stuff as well. Okay guys, so thank you, and next up is data representation.